is the one similarity this experiment had with off-world, but beyond that, you wouldn't build anything that looks like this at all. I'm supposed to say something else, but I can't remember what it is, so I won't let it go there. Any questions while we're in there? And when we have plants growing, and they've been growing here for 25 years, some of them grow pretty fast. And obviously we don't want anything poking out through a window. A lot of things that are growing here, though, don't exert that much force on them. Things like vines, for instance, they'll get up into the space frame. But nonetheless, we have climbers that go up, a few more up on ropes, and they'll go down, and they'll be the windstorm. They'll be the thing that takes things down that either should come down in a good windstorm or need to be trimmed because they don't want them poking through. But especially it's important not to get too dark in here. And what happens, we have vines that can get above the canopy up into the space frame. And that's an advantage they don't have in the real world. They have to fight for light, compete with light in a real canopy. Here they get up there, they'll hog all the light, they would just take over. Can't have that. So when we cut those vines down, we're not removing that material. If you look behind you here, you'll see this brown mass of stuff hanging down. That was vines, not too long ago, up in the space frame. We need the carbon that's stored in there. So we'll have new growth down the road. So we'll take that material, just let it rot. It becomes carbon in the soil, and then microbes in the soil flush that out as carbon dioxide. And now we have new carbon dioxide for plant growth down the road. It's wind one of the things we don't control. Great wind. We do not. Our electric bill is bad enough as it is. The issue with that, of course, is that trees and plants, when they grow up in windy conditions, develop something called stress weight. And that's primarily in the bark. And so when the next windstorm comes, the tree has the ability to withstand having it being bent over and so on and so forth. Our trees don't do that. Our trees can't even hold themselves up most of the time. We have to strap them up, or they'll break, the branches will be breaking off because we have no stress weight in there. So it has been, it hasn't had a big effect. But we also knew that that was possible, and so when we walk around through here, I don't know if you can see it here, when we walk around, you'll see some tree branches are held up to the space frame by ropes, just to keep that from happening. But that's the only negative effect on the road. If we had wind, here's the problem. We had no barriers up initially. We have 26 air handlers that allow us to control climate in each one of these 5 zones. If we had wind, we'd have no ability to control because we'd have too much mixing. So because we have so many air handlers, we're overwhelming the normal mixing of adjacent airspaces. And we can only do that because we don't have them. Yeah, right. Well, yeah. If we were studying ecology, there's a lot more things we'd have to pay attention to. Right now, we're studying how these plants respond to different climates, and we're also measuring at the same time, for instance, how fast carbon passes through a system like this. We're injecting a carbon isotope right now into the air. We have measuring devices that tell us when that carbon shows up in different places in the soil and in the trees, and then right back out into the atmosphere again. Those kind of experiments don't require having pollinators, none of those kinds of things. It's really kind of raw, basic response of plants, and not just a single leaf or a single tree, but we have the whole thing here. And so as Kobe University scientists used to say, they used to, when working with growth chambers, and they could do high CO2 experiments on a small scale, they would always have to scale up the results to try to mimic what goes on in the real rainforest. But here we don't have to scale anything up, we've got the real thing. So that's its advantage. But the kinds of things that we studied before the ecology, we're not doing that. It doesn't require knowledge of what animals are in here anymore. We have no idea what's in there anymore. We kind of took over this space and used it for something different. A little warm in here. Let's head to the ocean. Last person out, do me a favor and close the door behind us.
No, see, because this building was excavated, and then over there, concrete is concrete. Then it's going to be more concrete. So we're calling it ship on there. What's the next one?
Yeah, we do. Visually, you can see we still have ants. If we take a night tour in there, you'll see we still have lots of cockroaches in there. Which are a good thing. Cockroaches in the rainforest, they are detritivores. They actually have a function. They do chew up all the stuff that's on the forest floor there and turn it back into stuff that will eventually become carbon and nutrients in the soil. So cockroaches are a good thing. But visually, that's pretty much all we can identify. We've got ants and cockroaches. I've also seen tree frogs, lately slugs and snails, things of that sort. But we don't have a count. We haven't had a survey done since 1995. Really not much idea. Now, where we do know what's going on is this ocean right here. This is a different deal, and I'll talk about that in a second. But I need to answer a question first, and I'll answer it with another question. Show of hands, if you will. Who thinks that sounds like a whale? Not much support for whales today. All right. Who thinks it sounds like a dinosaur? You and I know what dinosaurs sound like, right? Okay. Sounds like that. I've heard of it. I think this woman came much closer to the answer. Who thinks it sounds like a wave generator? There you go. That's the smart money there. We needed waves in this ocean because it was built and designed as a coral reef. And a coral reef has all sorts of animals that they can't swim and get food. They're all stuck to the bottom. That's where they live, on the bottom. And if you want them to survive, you have to bring the food to them. And you do that by moving the water around. The real ocean, of course, there's all sorts of things that do that. You get waves, you get currents. In here, we'd have a static saltwater pond if it wasn't for this artificial wave generator we have here on the right side. We're lifting ocean water up above sea level up into a chamber. About every 10 seconds, we've collected about 10,000 gallons of water, which we then just drop. And that dropping water causes a pulse to come out of that chamber, which travels then as a wave from the deep end here on the right, clear across, past the reef in the middle, and up past the breakwater and up onto the shoreline there. Tiny little waves. You couldn't surf on these waves, but if you look to your left, you'll see in the reflection of the water, you have these little pulses coming across. That moves the water around pretty good. This ocean has been productive for us, but it's also been a problem. The expense-wise, this has been one of the more expensive ones because of the nature of coral reefs in the Caribbean. Water temperature just doesn't change much. About a narrow 4-degree band, and we spend about $200,000 a year keeping it at the right temperature. Well, we wanted to have a coral reef growing at 3,900 feet altitude. If you want something that exotic, you're going to pay for it. But we don't have that kind of money anymore. We're no longer a private company. We don't have those kind of funds. So there's a number of things going on to change this ocean. We lost the corals somewhere between 2003 and 2007. When I left here in 2003, we still had corals. When I came back much later than that, but in 2007 people reported that by then it was nothing but algae in there. So one of the things we had to do to keep coral reefs healthy was to have divers come in all the time and keep them from being covered up by algae. And we have an algae problem, not that we have algae in the Caribbean environment, but because we don't have any UV light coming through the windows, we don't keep algae in control here very well. We had to do it with divers going in instead, harvesting the algae up, keeping the corals from being covered up. But before we lost the corals, we did do some pretty good work. In the mid-90s, we studied the effect of ocean acidification on corals, saw how it affected their growth rates and health, recorded that information, published it, peer-reviewed, and that was 20 years ago. We now need to rebuild this ocean. One of the problems, not only did we lose the coral reef, the problem is that when we populated these different biomes, we were putting in complete food webs, but only of a certain size. You can't have anything like a mountain lion running around here, so we, in the rainforest, had like an 8-inch gecko, and everything else was much smaller than that. But it constituted the whole community of animals that normally keep each other alive. So this system here came from Belize. We brought up a community of animals that normally keep each other alive. The only issue with that is we don't have the advantage on the outside of Eventually, if something disappears because it becomes extinct or whatever, or disappears from an area, out there's wind, there's rain, there's migration, all kinds of ways of getting new genetic material to come back into that area. In here, we don't have that. If we lose something in here and we don't replace it, it's gone. And the problem is in the foods, in the animal populations, because we're not really studying them anymore, we have allowed holes to develop in that food web, and when that happens, the whole thing starts to collapse, because whatever was dependent upon one thing, you lose that as well, and then you start losing everything. So instead of having several thousand animals in here, including the corals, we're down to 15 fish. Not viable. Not something you could study. We don't want to turn it into an aquarium, but we do want to rebuild it, but not as a coral reef, but as a model of the Sea of Cortez. That's a much closer resource for us than any coral reef. It's just 6 hours south of here. It's also called the Gulf of California. Our reason for doing it, first of all, we'd like to do research in a body of water that is related to something regional to us. We've got issues here with freshwater, saltwater in this area, both northern Sonora and southern Arizona. So we'd like to do work in here that relates to those issues. We also need to save money, and I can tell you this. I've been diving down in the Sea of Cortez. You get down there in January and hop off a dive boat off of St. Carlos, you're going to be hopping into about 55-degree water. Not that unusual. But you go back 6 months later and hop off the dive boat into bath water. 92 degrees in that ocean. Unbelievable change. 40-degree temperature differential. And interestingly, you see the same animals and the same fish year-round. They don't migrate, they don't hibernate. They can tolerate much wider swings. We won't have to heat this anymore. That's the basic idea. There's at least $200,000 that we won't have to spend running this as a different model ocean. It's going to take a high capital cost, however, and that, of course, is holding us up at the moment. It's going to take a lot of money, millions of dollars to change this ocean out. This is the biome that got away from us. This was the savanna. Savannas are grasslands. You've seen the film Lion King, you kind of get the basic idea. A lot of grass, just a couple scraggly trees here and there because there's not enough rainwater for trees. You know, what's wrong with this picture? Nothing but trees. And here's the swing, by the way. I was talking about how we swing stuff up. There's one of them right there. This biome got too much rainwater. And it's not because we did it intentionally, but we have another rain system in here, if you will, that's drip from the ceiling. Pretty high humidity in here. When this glass gets cold overnight, wintertime, water condenses on the underside of this and starts dripping down like crazy. It's not as heavy as our rainfall, but it's significant. And over time, because of the shape of the ceiling, a lot of that drip came right down to this area, and these trees loved it. These trees took that rainfall and outgrew the grasses, shaded the grasses out, no more grasses, nothing but trees. But it doesn't matter as much. Back when we were running this as a closed system and people were living inside, we had to make sure we were growing our oxygen the whole year round. Not just summertime, not just winter. So we had a diversity of biomes to make sure that we always had something leaking out at some point during the year and always producing oxygen. It's that level of detail that we got into that we thought we had it pretty well figured out, that we could have 8 people come in here for 2 years, get enough oxygen to breathe, get enough food to eat. Didn't happen. People in the first mission were suffocating and starving. It was a brutal time for them. They didn't leave, but it wasn't pretty. And we'll talk about specifically what happened to the oxygen in here, where it disappeared, why it disappeared, and what it looked like once we found it. Kind of an interesting story. We're going to talk about that though at our next stop over in the desert. So while we're still here in this area, any questions about all this? Dead silence. Okay. I can handle that. I'm going to lead the way. We're going to walk to the off in this direction.
it's exactly my point. The person who recommended it, the first time I ever heard about this, was the ex-president of U of A in Arizona. And I didn't know who it was. He was on my tour, and he's chatting along, talking, we have a great time. And he said, you got to read The Martian, and do it with Blue Martian. Well, that has helped me out. I haven't done either one yet. And I didn't know the guy was on my tour. It was like a total freak out when I found out who this guy was.
We had hoped to balance out our atmosphere so it was conducive to life and everything that was in here. It took us a while to figure it out, though. We didn't get it right off the bat, that's for sure. We went from 21% oxygen in the first mission. At the beginning, we had dropped all the way down to 14% oxygen by 18 months into the mission. Now, you can live in that. It's not going to knock you out, but it's tough. It's like being at 13,400 feet if you've been at sea level. You're going to, until you adapt, you're going to be struggling. You're going to be, it's hard to get anything done, any work done. You climb upstairs, you're catching your breath all the time. But it was not the problem. The problem, the emergency, came because of what 14% oxygen does to cognitive function. We don't think very well under lower oxygen, and we had Biospheres reporting to the outside that they couldn't even do simple math in their heads anymore. And that's a danger because in a very building, this building being very complicated, you can't have people running it who can't think straight. That's just asking for trouble. And so by protocol, just to keep them from harm, we either had to pull them out in the mission early or we were going to save the mission and pump oxygen in, and we went with that latter solution. We brought a whole tanker truck up here and emptied it and into the west lung, brought everything back up to around 19%, which is pretty livable. You can live in that pretty easily. Several things were going on. The most obvious one involved sunlight, or in our case, the lack thereof. We built this place here in southern Arizona because we normally don't get many clouds, especially in the wintertime, bright blue skies every day. But occasionally, when El Nino shows up on the west coast of South America, we start getting a lot of clouds. And in the winters of 92 and 93, back-to-back winters, we had a lot of clouds due to El Nino, and that really messed us up. Because we had calculated the photosynthetic rates in here providing enough oxygen and food for people, and when we didn't get enough sunlight, we weren't getting that amount of oxygen or food. Hence the suffocation and starvation part of this story. We pumped oxygen in, and we only solved one of the two problems. We were willing to import oxygen, but we weren't willing to import food. So even though people were thinking a lot straighter, they were much more aware of how hungry they still were. Because you can't fix that. I mean, we were completely dependent upon it. We had no other auxiliary source of light for the farming area, and so for the next 6 months, people were still getting up from the table every meal, still hungry. It gets pretty old. We had another issue with oxygen, far more fascinating to scientists because they couldn't explain it whatsoever. They observed what was going on, but couldn't figure out why it was happening. And what they were observing was that in a mass balanced set of calculations, we realized we had lost track of 7 tons of oxygen. We can't lose oxygen or anything else in a closed system. That's the whole point of it. You put something in here, it's got to be in there somewhere. But it might not be in the form that you would expect it to be in. Therefore, we started thinking outside the box a bit, and suddenly it seemed to make sense that the oxygen was going into the concrete. May not make sense to most people, but it is an unusual phenomenon because concrete has 2 stages of being, if you will. You have the set concrete, 14 days you've got solid concrete, but depending on the thickness of the pour, and in our case, we have some 2-foot thick walls, that concrete could be still curing several years later. And that curing is a chemical reaction. Well, no one's really thought about this before, that if you build a building somewhere that you're absorbing or having an effect on the atmosphere. And we didn't think on a whiteboard that it made any sense that oxygen was directly going into the concrete, but we could see where carbon dioxide was capable of a reaction with curing calcium hydroxide. And when we had 14% O2 around here, we also had 10 times the normal amount of CO2. So a high concentration of CO2. How that affects the oxygen is that, of course, CO2 is 2 oxygen atoms within each carbon dioxide molecule. And so therefore, through that transport, we were losing oxygen into the walls. That was the theory. We turned it into practice when we investigated this. We got everyone out of here safely at the end of the 2 years, and we brought in a concrete coring company. We pulled some 3-inch cores out of some of the walls, and saw exactly what we had predicted on a whiteboard, that we had a significant, anywhere between 8 and 11 inches on the inside of our walls, just packed with calcium carbonate, which was the smoking gun for this reaction. And so therefore, the oxygen was being absorbed, if you will, by this whole process, and the walls weren't going to give it back anytime soon. We had another mission beginning very quickly, so we solved the problem simply by spraying the walls, sealed them up. We had a rig that kind of looked like a big spray gun, very, very thin water-based material, sealed the walls, end of story. Didn't have that problem anymore. So mission 2 had an easier time. We had fewer clouds, that helped considerably. But we went from 21% oxygen at the beginning, very quickly dropped down to 19.5, and there it stayed. And that was the success we were looking for. We didn't expect it to be perfectly balanced, but as long as it wasn't dropping precipitously the way it was the first mission, we considered that a victory. So we had that under our belt as something we solved. The food issue also got a lot better. Didn't hurt that we had a lot less clouds, but we also were cheating a bit. The second time around, we took the time to install 75 growing lights into the farming area, electricity driven. We weren't fooling around second time. If you think about it, if you're going to be living inside of a place like this for a couple of years, the last thing you want to do is do it hungry. Stressing out and being hungry at the same time produces all sorts of problems, and it definitely was. So we added the grow lights, and therefore there was far more food. Whether there was clouds or not, we were growing more food, and it really was quite a bit of difference. Near the end of the second mission, we were sending in groups of people in addition to the original group, 3 at a time. We called them gamma missions that were in for 1 week. And when these folks came in, we had all the apartments completely populated, all 10 apartments, and we still had no problem with food, had no problem with oxygen. It was a much more resilient system once we made those changes. A glaring example of this change in food is if you go into the upper habitat, you make it up there, go into the kitchen, there's a loop, video loop playing, and in the loop you'll see Biosphere, both mission 1 and mission 2 people picking up their food from the cook, but in very, very different ways. In the first mission, the cook has already served out in a portion control bowl everyone's food, so that everyone at least got something to eat. People were too hungry to trust that they could serve themselves at that point. In mission 2, same countertop, but there's big bowls of food sitting there waiting for them, and people could serve themselves, they could eat as much as they want. Totally different paradigm, different situation. So when we stopped having people live inside, we had been up to that point spending about $10 million to do so, and we felt that at that point we really weren't going to learn enough to justify that kind of expense, and therefore let's go and use this building for something completely different and move on. Any questions about that part of our history? Yeah. Was there any effect on their bodies? One might think, huh? 2 of the people exhibited signs of unusual nervous system behavior. They both had little head twitches. When they were investigated, CAT scans were conducted, there's a little part of the brain in the middle that's pretty much at the top of the spinal cord that was showing signs of calcification. And that calcification in one person led to head twitches, no big deal. In the other person, it seemed to augment conditions of Parkinson's and ALS, and eventually Roy Walford died in 2003. And when he died, he had the most unusual gait in the world. He was getting by, but simply by fooling his body into being able to walk. He would literally have to get himself just, okay, I'm lifting my legs up, and then something would kick in, and he starts slowing down. Then he